the S parameters of the strip line are already there, followed by a bend. Say your strip line comes this way and bends this way, right? Or your bend is mitered, like this, right? So you pick the right shape and you put it there, right? Followed by another strip line, all right? So you can scale all these S parameters in a SPICE-like package, and you push a button or click execute, and you get your S parameters of the combination, all right? That kind of thing. The one that was used in the lab, I believe it was, it's a QU, I can't pronounce the name, QCOX or something.
Oh yeah,
like that,
Quarks.
huh? Quarks?
That's what I said.
Something like that. It's a freebie that works just as well, and you don't have to pay $50,000 to get it. You know, the ADS, I believe, at some point, when we may still have a site license with the ADS, but you have to be on the university network to be able to use it. Well, this other package here, you can use at home anywhere, and it has all these built-in models for different shapes, you know, and you choose your parameters, and it helps you out and puts it there. So anyway, with all this kind of talk, what kind of shapes are typical to be used? I showed you the shape of the strip line, which is the hardest to fabricate. The easier one that's more typical is the microstrip, which is half a strip line. Now, this requires, or the configuration that you have here assumes that you have air on the top, right? You know, you have a microstrip or a strip width of W. Again, you will see that the expressions here neglect the thickness. There are other expressions that consider the thickness, and basically it's sitting at a height D from the ground plane, which is a typical situation. Now, most of the boards nowadays are not single layer, by the way. The shapes that I showed you so far is a single layer. Most of the shapes that exist nowadays are multi-layered. In other words, you have dielectrics everywhere and strip lines everywhere, and you may have so many layers of your circuit, and there may be some VS coming from here to there, a VS coming here from there, a VS coming from here to there, etc. These kind of shapes obviously get too complicated for this kind of analysis, and they require, and even clocks cannot handle anything like it. You know, when you have shapes like that, these are special designs that require that you resort now to the numerical tool itself to do the structure simulation. These are some of the typical expressions that you have, approximate ones, all right, for the microstrip. The microstrip is the one that almost everyone works with most of the time and gets discussed the most in the literature. As you can see, epsilon effective is almost equal to the average of the two epsilons. Epsilon of the dielectric below and the epsilon of the dielectric above, which is air. So if you are working with FR4, FR4 has dielectric constant of about 4. So you say 4 in the bottom and 1 on the top, that's 5. Square root of 5 is about 2.25, right? If that's built on Teflon, Teflon has dielectric constant of 2. 2 plus 1 is 3. Square root of 3 is 1.7, right? So that's how you get the epsilon effective here in the expressions that we use. And Z0 is equal to that expression here. It uses epsilon effective. And again, as you can see, some weird numbers, 8D over W and W over 4D. All right? Like I said, these are all, and that's only for W over D less than 1. If it's W over D greater than 1, then you have that kind of expression. And again, you see expressions here like your alpha D and alpha C. Alpha of the dielectric and alpha of the conductor. You notice here in the conductor and dielectric alphas, the material properties are there. Alpha and the conductor have this R sub S. R sub S is what we call the sheet resistivity of that conductor, all right, which accounts for the skin depth in that particular conductor. Right? And most of these numbers are known for typical material that are used in the manufacturing. Like, for example, in the printed circuit boards that we work with, most of the time, like I said, using copper. The copper in there, obviously, is one of the famous numbers that you find almost everywhere in any book. You open the book and you see a number for copper. Well, as it turns out, that the copper used in this case here is a rolled copper, and it's being processed to make it thin and flat, and that process changes its resistivity. So it eventually ends up with to be more resistive than the pure copper that typically you get. So you have to look for that particular number for copper under the sheet resistivity, because it's that particular process copper in this regard. Alpha sub D have the typical tan delta. Tan delta is the loss tangent of the dielectric, which is, you guys remember what tan delta is? The ratio between epsilon double prime and epsilon prime, right? That's your tan delta. So epsilon double prime was related to the conductivity of the dielectric itself. Okay. Here, in this effort here, in page 187 of this, like I said, an approximate electrostatic solution. What do I do with it? All right. We know it's approximate, so might as well take the approximate numerical solutions. Well, the reason for looking at these kind of things is okay. The reason for looking at this kind of thing is give you a feel for the complexity of the situation, as well as give you also orders of magnitude. Sometimes you need to get a feel for, is my simulation right? Is my measurement okay? So you need to have an order of magnitude for that. Now, the rest of these notes are already posted on the Scholar site, and also it has a section here. Let me just show you the pages that I covered from this book, Computer Aided Design of Microwave Circuits, by Casey Gupta and a couple of other people. And it shows how to deal with these kind of things in computer-aided packages, right? So there are lots of pictures here on how eventually it gets dealt with. So it's a good read. You're not going to get tested on any of this, but nevertheless, you need to know that information. Other shapes of line, the dual microstrip, the coplanar, kind of equations that typically are used in this, and approximate shapes that you need to work with. So please read that section. All right, don't say it's not going to be tested on, but you're not here for the test or for the grade, right? You need to arm yourself with this kind of knowledge so you can be less dangerous when you get out. Thank you.
Oh, okay.
Well, but
It's hidden somewhere in there.
it's this one right here.
I mean, I know I didn't
I mean,
write a whole lot with it.
Just
But I mean, the solution online is like pretty much exactly the same as that, so.
Show me that you understand.
Okay.
Okay? And
All right.
Will do.
Okay, thank you.
I have an option on now. From now or come after 1 o'clock?